Hello everyone. In this set of videos, we'll be discussing more about transistors. So before even entering into the world of transistors, let us try to understand why do we even want to look into it. Okay. So if you open any of the modern day devices like CD players, hard disks, pen drives, laptops, any one of them, you see a square box that is sitting over there with some pins which is surrounded by it. So that is what we call it as a chip. So here's the point where everything comes on, where the word transistor comes on. Let us try to find out a relation between this chip and the transistors. Okay. So what we'll do is we'll open up this particular chip and see what is there inside it. So for example, this chip will have some gates. It will have some logic gates. It could be a NAND gate, a NOR gate, an AND gate, or anything. It could be anything. So these gates are connected in such a fashion to achieve the desired functionality. So this is what you see when you open up a chip. This is the real thing the real circuit that you see when you open up a chip. So now these are the abstract level behaviors of something else. So let us try to first open up any one of the gates first. When you open up the gates, for example, let's say we will take the gate A5. If you open up that one, it's nothing but it's made up of CMOS inverters. This is what we call it as a CMOS inverter. We'll be getting into details of that, so let's not worry about that at this point of time. So this consists of a bunch of PMOS transistors at the top and NMOS transistors at the bottom, and this is how you achieve the functionality of a CMOS inverter. And there is a reason behind this structure of the CMOS inverter. We'll be getting into that in some time from now. Let's not worry about that. So let's try to understand what is there inside a chip and why do we even want to look into transistors. So here's where it comes from. So once you open up a gate over here, a gate which is let's say A5, it has got a bunch of PMOS transistors at the top and a bunch of NMOS transistors at the bottom. So using some combinations of PMOS and NMOS transistors, using some connectivity features of PMOS and NMOS transistors, you build up you come up with a NAND gate. Similar fashion structure will be present for a AND gate or a NOR gate or any of the gates that you see. So here the word transistors comes from, and this is what you see is the symbol of transistors. When you actually expand the transistors, this is what you see. So this is what you see. You have the source terminal, you have the drain terminal, you have the gate terminal, you have the body terminal, you have the substrate, you have N plus doping over here, and so on. So this is what you actually see. So any modifications of the electrical characteristics of this NMOS transistors will eventually go and affect the functionality of the chip. So now you understand the relation, that why do we even want to why there is a need to learn the word transistors. So that's why we start from this point and eventually we end up building a chip. So if you try to tune up this particular transistors in a fashion which is working, you find that your chip will be working. Any failure in any one of the transistors out of the billion transistors that are present on a chip, any failure in one of the transistors, in one of the electrical characteristics of the transistors, will eventually fail your chip. So that's how important the transistor is. So the one who is building the chip, he needs to know a lot about these transistors. If he understands the functionality of the transistors very well, so switching from this point till this point will not be a big deal. Okay, so let us try to understand this particular transistor from scratch. Let's say, so we have taken the N channel MOSFET transistor. We have taken the N MOS transistors for our illustration. And the inverse explanation for the NMOS is true for PMOS. So let's try to understand what NMOS is, and let's try to learn it from scratch. And by scratch I mean from the number of terminals that it has. It has got 4 number of terminals, and also we'll start from a box. A box is like we'll call it as a box. We'll call it as a p-type box over here, under which we are going to build the transistors. Okay, so this p-type box is called as a p-type substrate. So how do we obtain this particular p-type substrate? It's just a piece of silicon in which we dope p-type metals, basically in which we insert more and more p-type materials. So this is how it becomes a p-type substrate. It's as simple as that. So these are more of the fabrication terms that we'll be using, but we'll be not learning detail about the fabrication terms. But yeah, p-type substrate is nothing but a piece of silicon which has got a lot of p-type materials in it. It's as simple as that. Okay, so you start with the p-type substrate, and then next what you do, you create some isolation region at these sides. So this bulk of silicon dioxide is nothing but isolation, acts as an isolation region. And why we call it as isolation region? The reason is in the center point that you see in this area. This is the area where we'll be building the transistors, and this particular transistor will be isolated from the other transistors using this blocks of silicon dioxide. They could be connected, these transistors could be connected to the other transistors via some wires over here, via some metal connectivity over here, but they would not be physically connected from this transistor to this transistor. There will be some isolation that will be present across adjacent transistors. So that is the reason you have this isolation regions over here, and this is the area that we call it is an active area. So this is the area where we are actually going to build our transistors. Okay, so now what we'll do is, when we say about NMOS, it's nothing but N channel MOSFET transistors. So basically we have to create an N channel. So let's see how do we do it. So next you do it, you diffuse N plus dopants, or what you call it as N plus impurities inside the p-type substrate. In this fashion, in this small area and in this particular small area, you dope it, you diffuse N plus type impurities over here, and while maintaining a small piece of gap over here. So how do we maintain this particular gap? There are some lithography techniques that we do it. So that's again a fabrication technology that we have to look into, but there are ways to control the diffusion of this particular dopants inside the p-type substrate in this area. So there are methods where we can stop the impurities from entering this area and allowing the impurities only entering into this areas. So this is how we get this particular N plus and N plus kind of diffusion region. Okay, next what we do is at the center area where we have kept some open space, we build a gate over here. We build the gate oxide over here. We actually grow a gate oxide over here, and this oxide will act as an oxidation or as an isolation element between the gate which is present over here, which will be a metal gate, and the substrate. So when we say NMOS, it's N channel metal oxide semiconductor. So this is where the name comes from. This is the metal, this is the oxide, and this is semiconductor. So it's metal oxide semiconductor, and there are reasons why we do it. So those are device physics related reasons which we will be not be covering in this particular section, but in some other sets. So this is where the name comes from. This is metal oxide semiconductor, and we have this N plus source and drain. So this N channel will be created between the N plus source and N plus drain, somewhere in between. So we'll be coming into those things, so let's not worry about those terms right away. Okay, so this is how you build the N plus diffusion area, and you have the gate oxide over here, and you have the gate over here, basically a metal gate. So now let us try to build the terminals. So this particular terminal will be called as gate, this one will be calling as source, and this particular terminal will be calling as drain. Usually when we draw a transistors on paper, you see there are only 3 terminals, but in reality there is a 4th terminal that is present, which we call it as body. which is present over here, and this particular terminal affects the electrical characteristics of the MOSFET. We'll be looking into how does it affects the electrical characteristics, but we should always remember that there is one more terminal which is sitting over there, and that we call it as body. So since I'm running out of time, I'll let me stop over here. In the next video, we'll be looking into we'll be connecting the source, gate, drain to some potentials, and we'll be looking into some electrical behavior of this particular MOSFET. So let us try to stop over here, and let us try to continue from that point in the next video. Thank you.